In single variable calculus, we had a notion that a function f of x near a point x0 was approximately equal to its tangent line. Say f of x0 plus the derivative at x0 times x minus x0. Well, now when we have a function of two variables, say f of xy, then we have this notion that f of xy is approximately f of x0, y0 plus the gradient of f at x0, y0 dotted with x minus x0, y minus y0. So in other words, the function f of xy is approximately equal to the tangent plane near the point x0, y0. And so you have this symmetry. You can see that for a single variable function, that's approximately the tangent line. And then for this multivariable function, f of xy, that's approximately equal to the tangent plane. And so both of these tangent line and tangent plane approximations are called linear approximations. So let's do some examples involving linear approximations. So first, let's consider the function f of xy, which is equal to 2 minus x squared minus y squared. In the previous video, we saw that this function was locally linear and that it was approximately equal to the tangent plane near the point 1, 1. So we can say that if we wanted to find f of 1.1, 0.9, well, that's going to be approximately equal to f of 1, 1 plus the gradient of f at the point 1, 1 dotted with 1.1 minus 1 and 0.9 minus 1. Okay, so here we're saying near 1, 1, f of x is approximately equal to the tangent plane. So previously we saw that f of 1, 1 is 0. The gradient of f at 1, 1 was negative 2, negative 2. And then that's going to get dotted with 0.1, negative 0.1. And so here, this is going to be approximately 0 minus 0.2 plus 0.2. So it's actually going to be approximately 0 at that point, 1.1, 0.9. In fact, just to kind of verify as a check, if we actually plug that in, f of 1.1, 0.9 is actually equal to negative 0.2. So it's very close to 0. Okay, so this is a good linear approximation. Okay, now suppose we wanted to approximate, say, the square root of 15 and times the square root of 99. So in other words, we've got a function f of xy, and that function is the square root of x times y, or square root of x times square root of y. So we want to approximate the square root of 15 times the square root of 99 using some square roots that we already know. So maybe we want to look at f of 1600, because then we're looking at the square root of 16 times the square root of 100, which is a bit easier to calculate. That's going to equal 40. Okay, well, if we're going to do a linear approximation, we're going to need to compute the gradient. So what's the gradient here? The gradient of f, in this case, is going to be, let's think about square root of xy as being, say, x to the 1/2, y to the 1/2. So that the gradient, when I take the partial derivative with respect to x, is 1/2 x to the minus 1/2, y to the 1/2, leaving that y alone. Okay, and then the partial derivative with respect to y is going to be 1/2 x to the 1/2, y to the minus 1/2. And then let's plug in x and y being that point 16 and 100. Okay. So here, that first term, let's go ahead and maybe factor out the 1/2 just to make things easier. So that first term is going to be the square root of 100 divided by the square root of 16. Okay, so that's going to be 10/4. And then the second one is going to be the square root of 16 over the square root of 100. So that's going to be 4/10. So if we multiply by 1/2, okay, so we should get 5/4. And then 2 times 4/10 is actually going to be 1/5. Okay, so now we have the gradient. Okay, so we're going to have that f of 1516. That's going to be approximately, sorry, not f of 1516, f of 1599. That's going to be approximately f of 16/100 plus the gradient of f at 16 and 100 dotted with, in this case, 15 minus 16 and 99 minus 100. Okay. F of 16/100 was 40. That gradient that we calculated is 5/4, 1/5. And then we're going to dot that with -1, -1. So here we're going to get 40 minus 5/4 minus 1/5. Okay, and if we work that out, that's going to be 38.55. So then there's a good question, is that actually a good approximation? Well, if I do the square root of 15 times the square root of 99 and put it into a calculator, that's going to be actually approximately 38.536. So in fact, this is a pretty good approximation. We're only off by about 14 1/1000ths. Okay, so hopefully you noticed that I put this in a form with gradients, this tangent line approximation, this linear approximation, tangent plane approximation, or linear approximation. In fact, if you like, we can do the dot product. You'll notice that it looks like df dx times x minus x0 plus df dy times y minus y0. And you can see a nice symmetry here to the linear approximation formula above. Okay, so before we only had one derivative, so that derivative got multiplied by x minus x0. Okay, now we have two different partial derivatives. Okay, both of those are going to be multiplied by x minus x0 and y minus y0. Okay, going along with linear approximations is the concept of the differential. Now, the differential is written as either df or delta f. Okay, and that's going to be the gradient of f dotted with delta x, delta y. So the differential is in fact, it's just part of the linear approximation. Okay, so if we're trying to approximate something like f of x plus delta x and y plus delta y, okay, then the linear approximation would say that would be f of xy, okay, plus the gradient of f at xy dotted with delta x, delta y. Okay, so this part here of the linear approximation, okay, is df. Okay, so the differential is how much the function changes by when you do a linear approximation. And you see these differentials used often in applications, especially in things like chemistry or any sort of science where you're doing measurements. So let's look at two examples of using differentials. Okay? So the volume of 1 mole of an ideal gas is going to be given by volume equals 0.082 times temperature over pressure, where P is pressure and T is temperature. And we want to approximate the change in volume when P is increased from 2 atmospheres to 2.2 atmospheres and T is increased from 300 Kelvin to 310 Kelvin. So we've worked with this function in a previous video. Okay, V is a function of T and P. So the differential, okay, the change in volume, okay, is going to be dV dt, dV dP, so that gradient, dotted with delta T, the change in temperature, and delta P. So we want to know if we change a little bit of temperature, we change a little bit of pressure, okay, how's that going to affect the volume? Okay, so we're not going to actually say what is the new volume when we change that temperature and pressure. We just want to know how much the volume changes by. Okay, so if we take the partial derivatives with respect to T, we're going to get 0.082 over P. And then take that partial derivative of V with respect to P, we'll get negative 0.082 times temperature over pressure squared. And then we're going to dot that again with delta T, delta P. Okay, so now we're going to plug in some numbers. Okay, so here pressure is 2. So we're going to get 0.041. Okay, so here, let's make sure we understand that we're plugging in P equals 2 and T equals 300. And here we're going to get negative 0.082 times the temperature of 300 divided by our pressure 2 squared. If we do that, we're going to get 6.15. And we're going to dot that with the change in temperature, which is going to be 10 Kelvin, and the change in pressure, which is going to be 0.2 atmospheres. Okay, so doing that dot product, we're going to get 0.41 plus 12.3 in this case when we, dotted with 1.23. Okay, so that change in volume is going to equal 1.65. And this is going to be in meters cubed. Okay, so if we change temperature by 10 degrees Kelvin, okay, but also change the pressure by 0.2 atmospheres, okay, the overall change in volume is going to be 1.65 meters cubed. Okay, let's look at a different example with a volume. Okay, the length of each side of a metal cubed is going to be measured at 10 centimeters, but the error in the measurement could be as much as 0.1 centimeters. So we want to use differentials to estimate the maximum resulting error in the calculated volume V equals X, Y, Z. Okay, so here we're going to calculate the volume. That volume is going to be 10 times 10 times 10, so 1,000 cubic centimeters. Okay, and we've measured each of the sides to be 10 centimeters, but they could be off by essentially a millimeter, 0.1 centimeters. We want to use differentials to figure out, well, how far off could the volume be? Okay, so the change in volume, that's going to be the gradient of the volume, so that's df dx, df dy, and df dz. Okay, dotted with delta x, delta y, and delta z. Okay, well, df dx, okay, the derivative of, oh, those are not f's, those are v's. Okay, dv dx, that's going to be the derivative of x, y, z with respect to x, so that's yz. dv dy, that's going to be the derivative of x, y, z with respect to y, so that's xz. And then dv dz, the derivative of x, y, z with respect to z gives me going to be xy. And we're going to dot that with delta x, delta y, delta z. Now, yz, that's going to be, let's see, so we're going to know x, y, and z are all measured at 10 centimeters. Okay, so y times z is going to be 100. X times z is going to be 100. X times y is going to be 100. And then we're going to dot that with our possible error in the measurement of 0.1 centimeters. So 0.1, 0.1, 0.1. Okay, so that when we do that dot product, we're going to get 10 plus 10 plus 10. Okay, and our change in volume in that case is going to be 30 centimeters cubed. Okay, so we have essentially that our volume is 1,000 centimeters cubed. Okay, but it could be off by as much as plus or minus 30 centimeters cubed. So you might see someone write the volume is going to be equal to 1,000 centimeters cubed, maybe plus or minus 30 centimeters cubed, based on the fact that the dimensions are each 10 plus or minus 0.1 centimeter. I want you to notice that the units worked out in this case. You can see that this is in centimeters squared, this one's in centimeters squared, that one's in centimeters squared, and then these measurements of air are all in centimeters. Okay, so when we do the dot product, we do get centimeters cubed. And so differentials are often used to help understand what the errors might be resulting from error in measurement.